Magnetic field around current-carrying conductors. Hans Christian Ørsted, a Dutch professor, discovered the magnetic field around a wire carrying current while performing a classroom demonstration of the heating effect of electric currents. He observed that the needle of a nearby compass deflected and the needle returned to its normal position when the current stopped flowing through the wire. He concluded that there is a link between electricity and magnetism. Want to see the deflection? Arrange a battery, ammeter, key, and a copper wire as shown here. Place a magnetic needle below the copper wire. Switch on the key and observe the magnetic needle. Now, switch off the key. We observe that the magnetic needle swings when the key is switched on and comes back to its normal position when the key is switched off. The magnetic field around a conductor can be mapped by using iron filings. Let us now trace the magnetic field pattern around a current-carrying straight conductor and a circular coil. Arrange a copper wire, reversing key, rheostat, battery, and a thick sheet of cardboard with a hole at its center as shown here. Sprinkle some iron filings on the cardboard. Now, gently tap the cardboard to overcome the force of friction and inertia of the iron filings. Observe that there is no change in the arrangement of iron filings. Now, switch on the current. Observe that the iron filings arrange themselves in concentric circles around the conductor. This is because the electric current produces a magnetic field around the conductor, and the iron filings, being magnetic in nature, align themselves in concentric circles. Place a small magnetic needle in the vicinity of the wire. The direction in which the north pole of the needle points indicates the direction of the magnetic field at that point. Observe the magnetic field pattern when the direction of the current is reversed, and also when the strength of the current is increased. The direction of flow of current is changed by rotating the arm of the key. The needle of the compass deflects in the opposite direction, indicating a change in direction of magnetic lines of force. On increasing the strength of current in the conducting wire, the number of lines of force around it increases. Right hand thumb rule. Imagine the conductor to be held in your right hand with the fingers curled around it. If the thumb points in the direction of the current, then the curled fingers show the direction of the magnetic field. Maxwell's corkscrew rule. Imagine a right-handed corkscrew being rotated along the wire in the direction of the current. The direction of rotation of the thumb gives the direction of the magnetic lines of force. Ampere's swimming rule. Ampere's swimming rule states that if a man swims along the wire carrying current such that his face is always towards the magnetic needle, with current entering his feet and leaving his head, then the north pole of the magnetic needle is always deflected towards his left hand. Make 2 holes in a sheet of cardboard. Pass a thick insulated copper wire through the holes as shown here. The ends of the coil are connected to a battery through a rheostat and a reversing key. Sprinkle some iron filings on the cardboard. Switch on the circuit. When the current is passed through the coil, the iron filings on the cardboard align themselves with the magnetic lines of force of the current-carrying coil. Observe the magnetic field pattern when the direction of the current is reversed, the strength of the current is increased, the direction of flow of current is changed by rotating the arm of the key. The needle of the compass deflects in the opposite direction, indicating a change in direction of magnetic lines of force. On increasing the strength of current in the conducting wire, the number of lines of force around it increases. The polarity of the faces of the coil depends on the direction of current and is obtained by a rule known as the clock rule. According to this rule, when an observer looking at the face of the coil finds the current to be flowing in the anti-clockwise direction, then the face of the coil will behave like the North Pole. While if the current is in the clockwise direction, the face of the coil will behave like the South Pole.